as introduced, my name is Homin Park. I'm currently a research fellow in NUS in Computer Science Department. So for today and tomorrow, what I'm gonna do is I'll give you a very long, like the seminar on the history of AI, and maybe and describe many different algorithms that we use in deep learning or AI technologies, and maybe give you more hands-on experience in the day two. But for today, what we're going to focus on is the history, and then I want to give you the definition of AI and machine learning. And I'm going to introduce you a few machine learning algorithms. Maybe you know some of them, maybe you don't know some of them, but I'm introducing them because those are essential, necessary algorithms that you need to understand in order to understand the artificial neural network. And in that, it's more of a deep, in order to understand deep learning, you need to actually know those basic concepts before we actually move on. For your information, if you have any questions during the talk, just feel free to raise your hands. I'll be more than glad to answer your questions or concerns meanwhile during the talk. So, okay, let's dive into the history of the artificial intelligence. So artificial intelligence is now everywhere. Like, whether you know it or not, we've seen a lot of movies about AI. Matrix has been there since a long time ago. If you know iRobot, that's also another AI movie. If you know Her, not the person Her, but then the movie Her, it's another movie that this guy here has a relationship with the AI voice. And then there's another movie with the Johnny Depp on it called Transcendence. There's a lot of games that incorporate AI technologies. Also the smartphones, if you use iPhones, Siri is AI. If you use Samsung Galaxy or any other Android phones, you also have those intelligent voice assistance programs embedded in it. And whether you know it or not, your email system has AI in it. The spam filters, I don't know whether you guys have used the very old-time email systems. Like, there's no such thing as filtering the spam. So you get your friend's email, on top of that you get a lot of spams and junk emails on top of it, and you have to manually delete them. But then now if you're using Gmail, it actually automatically and mostly intelligently remove those spams that you don't actually want to see. Another famous movie, Iron Man, also. Actually, a lot of computer scientists, people actually get inspired from the movie. A lot of technologies introduced there actually helps a lot to actually get inspired. If you know Tesla, it's an autopilot. It's a vehicle company in the United States that has autonomous vehicles. Also, there's a lot of medical services and much more. So these AIs now actually is making a lot of decisions for you, whether you like it or not. The IBM Watson Health is introduced by a company called IBM. What it does is it collects your medical history, or if you have any symptoms right now, it will require like blood test records, like the heartbeats, all that stuff, to actually make a personalized medical treatments for you. And then these treatments, you get it, and then you send it to, or the Watson actually send it to the clinician, and he or she will provide the medical service for you according to the suggestions. A lot of chatbots, if you're using Facebook or any other social medias. A lot of customer services right now has incorporated the AI chatbot. So when you're talking with the customer service, at the first you're not talking to the person, and then once the complexity of your concern or questions increases, then the AI goes, hey, please wait for a minute. I'll call the necessary personnel to handle your question. And the transition is quite smooth these days. And Amazon Echo, like a lot of smart homes, so-called smart homes, actually use those AI speakers to actually assist your needs. And then more to come is there's also baseball referees. And there's a lot of sports who actually where they employ AI referees because they can no longer trust human judgments on some cases. And then for the journal, like in LA Times, they actually incorporated because they had a lot of earthquakes there, and those incident report it actually requires the real time the broadcastings and everything. So these robots actually write those articles, and at the end it says it's robot generated. So it's pretty fascinating these days. Also, there is artificial intelligence for art. So there's a AI composer called Kulita, was developed by the Yale University. Actually, they tested it with the human subjects, and they cannot distinguish the actual music from Bach from the music composed by Kulita. So it's getting pretty advanced right now. And Google Deep Dream actually has painting AI, which actually, given the picture of a person, they can actually distort it or actually make it more artistic to actually make it pleasing, I guess. So, but if you go into that Deep Dream website, you can also, if you can search on a website, Google on that keyword Deep Dream, and see how they actually change those features. So I introduced you where the AI is used in our daily livings now. The state of the artificial intelligence right now is getting better every day. Google Deepface is a face recognizing algorithm developed by Facebook. It actually now can recognize human faces better than humans. I'll talk more about that in the later slides, but yeah. And then the Google Photos, if you're using Androids, they can automatically categorize your own photos into different groups without you actually doing anything. So they recognize what kind of photo it is, whether it's scenery, whether it is food, whether it is a person. They group them, and then whenever you want to see something specific, they can actually provide that information for you. Does anyone know the game of Go? So if you don't know, there's something called AlphaGo. Was developed a few years back. The game of Go is like a chess. It's not like a chess, but it's more complex than chess. There's two players in it, one against each other, white stone and the black stone, and they have to fight each other for that. It's known to, I mean, the chess, we consider that as a somewhat finite combination of play styles. But Go, people call it, hey, there's an infinite number of combinations of how you can play Go. And people thought that, AI can never actually beat human beings in game of Go because there's so many combination and play styles to consider. But hey, AlphaGo actually beat the top human players in year, I think 2015 or something. And then since then, no one has beat AI in this game. And now the game is actually it's declined. The business of the game of Go is actually declining these days. And even like your toothbrush Oral-B has intelligent AI embedded in it. Now they can recognize like how well you brush your teeth, and then they can suggest you, hey, you're not brushing your, I don't know, maybe your upper tooth not very well. Try to focus more on that. They can actually provide you those information. As introduced, Tesla autopilots and some of the voice assistant systems as well. So all this AI talks, like AI that, AI this. So what exactly is AI? So the AI is any computer systems that can correctly interpret the data. So here the external data, meaning the data from the real world. And to learn the patterns in the data and use those learned patterns to achieve specific goals. So for example, like the face recognition, like, I look like this, maybe everyone looks different, right? So the photo of us is the real world data. The AI learns the different patterns found in our faces, and the specific goal is to differentiate who am I, who are you, by just looking at the data, looking at the photos. Let me know if you have any questions, okay? So having said that, so I want to also cover some history of AI. So the concept of AI was first introduced in year 1956 in a conference called Dartmouth. And then there was a big boom. So in the 60s, there were a lot of people who studied AI. But then around year 70s, there was a big fall. We call it the first fall, due to the systems, the AI systems' incapability to actually solve the complex real-world problem. But in years 80s, so 1980s, it had another rise because a lot of researchers proposed, hey, AI could serve very specialized expert tasks, like estimating, for example, for your research domain for geotech, like estimating some properties of the soil, or maybe we're estimating or even for bank application, estimating how your income will be like in the next 10 years, all such things. So there was another rise. But in the 90s, there was another fall because those expert systems were not scalable. We saw that these specific AIs do okay job in the specific area, but none of these systems were scalable to another application. For example, if there's an AI specifically designed for your income estimation, it was not applicable for whether, let's say, whether you'll be able to estimate whether you'll be able to pay off your house or mortgage or something like that. So there was a second fall, but then there was a rise again. So it took almost 50 years for the computer scientist researchers to figure out what was actually wrong in the area of AI. So the old systems actually try to explain everything to the computer. Like, for example, like how to distinguish dog from cat. Can you give me all the rules how to distinguish them? Maybe fur type, maybe how their eyes look. But those informations are very intuition. Those informations are intuition-based knowledge. It's not something that we can verbally or mathematically explain to the computer. But that's what the old AI people try to do. So they figure out that doesn't work. So what they did was they got inspired from how human beings actually learn. We actually learn from data. We actually learn from experiences. So the conventional machine learning people incorporated a concept of self-learning. And then at that time, they had the very simplest idea of what deep learning could be. So they had the simplest idea on what the deep learning could be, but there was a lot of problems to actually make this technology successful. Mathematical problems, theoretical problems to actually make this deep learning successful. But in year 2012, a professor named Geoffrey Hinton actually solved this mathematical problem, and now he is one of the founding members of the deep learning technology framework. And since year 2012, now the deep learning and AI has seen the new rise. So touching on the so-called Moravec paradox is that for computers, like the tasks that are easy for computers are hard for humans, and tasks that are hard for computers, maybe it could be easy for us. For example, like if there is a derivative equation, very complex derivative equations that we need to solve, it might take a few minutes to solve it, but for computers, it takes less than a second. But then to recognize human face or to distinguish the dog from cat, we do it very fast, right? We just saw the picture and we can just definitely do it very quickly. But computers could not do that since before 2012, but now they do it better than us. So now actually they got much better. The next slide is a clip. I couldn't actually connect to the speaker here, but I actually turned on the volume so you could take a look at it there.
Deep learning neural networks learn many levels of abstraction. They range from simple concepts to complex ones. This is what puts the deep in deep learning. Each layer categorizes some kind of information, refines it, and passes it along to the next. Deep learning lets a machine use this process to build a hierarchical representation. So, the first layer, for example, with a facial recognition system, might look for simple edges. The next might look for collections of edges that form simple shapes, like rectangles or circles. The third might identify features like eyes and noses. After 5 or 6 layers, the neural network can put these features together. The result, a machine that can recognize certain objects or even concepts, dependent on the training dataset.
Yeah, that was a very brief introduction on how the deep learning actually works. So the reason why we call it deep learning is because there is a lot of layers, so we call it the depth of the network, depth of the algorithm. So as the network depth gets deeper, we call it deeper learning. But in general, we call it deep learning in general. But I will cover this in the later slides. But I just wanted to let you guys know the general concept of what the deep learning is. So maybe a little bit more of it is, so basically to use machine learning or AI or deep learning in general, what you need is a data set with labels in most cases. Sometimes you don't have the labels, but it's maybe if you have more questions on that, or if you have any problems having that you have the data set, but you don't have the labels, maybe you can contact me later. I'll try to advise you on that. But in this seminar series, we're gonna tackle the problem where you have the data set and you have the label there. So the label here meaning the answers. So you have a task question, or maybe you have an image. The label here means whether this image is a cat, whether this is dog. So the label is basically, you can also call that whole label as an information tag or answer that you're trying to look for. So from here on, whenever I say label, that's what could mean. The deep learning is mostly used for the recognition, classification, and sometimes for analysis and estimations. So basically, after the advent of the deep learning in the year 2012, AI is getting much better every day, and most of the field is actually getting better than human beings. The deep face, as I mentioned earlier, which actually recognizes human face, can recognize human with the accuracy of 99.96%. That's 1% better than human beings. So humans can actually recognize about 98% of the time, another human face about 98%. You will say 2%, where does that come from? But some people, when the image is distorted or when the image is blurred, there's the 2% error. But then the deep face, the AI actually performs much better, even when the image is distorted or blurred out. And then year 2015, the AlphaGo actually won the player, and since then no one has ever beat AlphaGo so far. So that was the introduction. So if do you have any questions on like applications of deep learning or history? Okay, feel free to let me know. Okay, so the next is the definition of the artificial intelligence and machine learning. So now it gets a little bit more techy. it will include a little bit more details. So the definition of machine learning was first introduced in the conference called Dartmouth by a researcher called Arthur Samuel. So machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. That was the initial concept, but now it's a little bit different. But in the year 1998, Tom Mitchell actually said the computer program is set to learn from experience E with respect to some task T and some performance measure P if its performance on T on measure by P improves with experience E. So what it means is that as the computer learns, it needs experience on the given task T. And the performance, whether it's doing a great job or not, it will be measured using some metrics P. Okay? So I have a quiz right after this. So okay? Actually, I do have a quiz. So definition is given here. So okay, let's assume this. Suppose your email program watches which emails you do or do not mark as spam. Okay? And based on watching you, the AI will learn how to better filter the spam in the future. So in this scenario, what is T? Okay, raise your hand if you think the answer is 1. Okay, raise your hand if you think the answer is 2. 3. Okay, you got it right. You got it right. Perfectly correct. So basically here again, so the experience, task, and performance measurements, right? So in this email program, watching you, whether you're actually marking an email as a spam or not, and it will actually has to filter those emails automatically in the future, right? The task that AI needs to do is classifying whether the email is spam or not. Okay? And what could be number 2? Any guess? Watching you label emails as spam. What is that? So this one was T. Is that a P? Is that related to the performance? Or is that an experience? So raise your hand if you think it is an experience. Great, okay. So that's an experience. So it's in terms of AI, not for us. Okay. In the perspective of AI, this is the experience. And then what is 3? The number of emails correctly classified as spam or not spam. That's a performance. Okay. So when you first think about, okay, so I want to use AI, when you first think about that question or that statement, you need to be able to actually formalize this concept. What is the task? What is the experience? What is the performance measurements? So once you have a clear idea on this, then you can move on to building the system pipeline, figuring out what algorithms to use. Okay. So I want to actually touch ground on the system pipeline, how to design them. So traditionally, who here that use MATLAB here or any other programming languages? If you do use one of them, so what we have is a data and a program. Program here means like you're sitting on the computer typing out the program, actual programming script, right? And then you program, let's say the program here could be a mathematical equation, could be ax plus b, linear equation. That could be one of the program. So given the data, which could be the x value, output comes out, the y. Okay? So here, data is x, program could be ax plus b, output is y. The computer it serves the job of just computing the values. But what machine learning does is it has the data and it has the output. What is that output? That's the label, right? In the previous slides, I mentioned that all you need is the data and the label, which is output, which is the answer. So given those two data and information, computer do some magic, and then it gives you the program, which is the ax plus b, the equation. Okay, so this is how the old way of computer science and the new way of computer science using the machine learning. But actually, even when they're different, you actually need to combine them together in the later in the phase. So let's say you want to build a machine learning system pipeline system or AI. You first need to provide data and output to figure out the program. Now, once this training the AI is done, let's say here the training meaning like I'm teaching the AI, hey, you need to recognize, you need to differentiate the cat from dog. That's the training So I'm training the AI. So once the AI says, hey, I'm confident that I can serve you now, right? You can now take that program, put it into actual practice, and whenever the new data comes in, that the AI never seen before, it will give you the output. We call that test phase. And that's where the system is deployed. Okay? So the machine learning, in a nutshell, is that there are a lot of machine learning algorithms available these days. In the past and in the future, every year there's hundreds of algorithms proposed in the AI conferences. But all the machine learning or AI algorithms have three components, which we call it the representation, evaluation, and optimization. This is also very similar to the task, the T, E, and P as well. So here the representation is the representation of the program. So how are we going to represent the AI's function? And there's a lot of representation techniques for that. One of them is neural networks, which we will cover later. Okay. And evaluation is related to the performance measurements. So how well does AI performs? So very simple. We can use accuracy to evaluate the performance. Squared errors, likelihood, and maybe the margin and entropy and all that other stuff can be used for this. So when the AI is evaluated, so let's say you took the test, you get the score from maybe when you're in the high school or university, you take the exam, you get the score. What do? You need to if you want to get better, you need to improve yourself, right? The optimization is the improvement. So how the AI will improve its performance? Well, the method depends on what kind of algorithm you actually use. So there's a lot of different algorithms that's being used for the optimization. And then in the machine learning, there's different types of learning techniques. And most of the learning techniques falls under these four categories, which is a supervised learning, unsupervised learning, semi-supervised, and reinforcement learning. For the sake of today's seminar, I'm gonna focus on the first one only. This one is where the data and the answers are available. This one is where only the data is available. But these two are most critical and most famous field of machine learning study. So a bit more about the landscape. So if you are actually interested in AI, you might also have heard the big data. You might also heard about data science, and machine learning, deep learning, and all that stuff. So artificial intelligence is a very big research area, but it is somewhat different from big data and data science, but they do actually overlap. So as you can see, when someone say, hey, I do AI, that is a very vague term. It actually covers so many different fields. When someone say, hey, I do machine learning, okay, so it's a little bit narrowed down this concept. The deep learning is actually one of the machine learning techniques to actually serve a very specific task. And the deep learning actually also requires a big data because the deep learning algorithms we call it the data hungry. So more data, more quality data you put in, the better the algorithm will get in the future. Okay, so that was the definition. So now what I'm going to do is I'm going to explain and illustrate 4 different algorithms. You might wonder why do I need to learn these algorithms? These are, personally, I think it is a 4 key algorithms that you need to understand in order to understand the neural network concept and maybe in the future the deep learning concept as well. So I'm going to cover the linear regression, logistic regression, k-means clustering, and support vector machine algorithms. You might have heard about the linear regression, but so I'm going to cover it anyways. So what is linear regression? Is basically a linear approach to model the relationship between a scalar response, which we also call it a dependent variable, and one or more explanatory variable, which we call it independent variable. So meaning x and y, basically. We learn the x equals the data, y equals the answer. So we learn the relationship between the data and the answer, and the relationship or the mathematical, the program, is actually expressed in a linear fashion so that it can be actually very simply used and estimated. And this, it falls under the what? Supervised learning, because we have the data and the answers together. Okay? So you might wonder, okay, I heard about linear estimation, I heard about linear equation. The regression is basically it's a concept where it's a measure of a relationship between the mean value of one variable and the corresponding variable. Meaning, so x and y, so we're actually computing the relationship, right? So the regression is a recursive method to measure how well this blue line fits these red dots, and as progressively the correctness, the accuracy of these blue lines gets better. So I will show you the example here. So let's assume that we have x and y here, and the x, the data, is 1 to 3, y is 1 to 3. Very simple linear regression algorithm, right? And let's say we also call this as a hypothesis representation. So we are hypothesizing, hey, the yellow line could work. Hey, black line, hey, it's the red line. So let's say we don't know yet. I mean, of course, conceptually, you know this one is the best, but you're actually talking to a dumb computer here, okay? So you have to tell the computer which one is better, not by just telling them, hey, this looks like it's better, but you have to, speak in a mathematical tone, okay? So the question is, which hypothesis is better and why, okay? In order to compute which one is better, we use a term called cost function. The easier way to understand this is basically it's an error. The cost function could equal to error. So basically it's the difference between the actual data and your hypothesis or estimation model, right? Doing all this gory mathematics, basically what it does is it actually computes the distance from the point to the model. So you see that there is a distance, different distances. What we do is we sum them all up and we take their average. So we call that a average error for the given program, given mathematical equation. Okay. More details. I'm going to actually give this slide to Dr. Kim later. So if you guys want to actually take a look at it and see how this actually works, I actually added a little bit more details if you want to actually dig into the mathematics a little bit more. So I talked about the linear hypothesis. Now we have to talk about the regression, right? So the regression part, as I explained, is a progressive steps that you take to actually make your hypothesis or the program perform better, right? So the error has to be what? The minimized. So here, this is the W, so meaning here you can see that it's W equals 0, W equals 1, W equals 2. Here you can see that this W is basically from the linear equation AX plus B, W is basically the A here. So if you know the linear regression, when the A is 0, the line is flat. When the A is 1, it actually increases linearly. So every time the X increases 1, the Y increases 1, and goes on and on. And when it's 2, it increases twice as much. So given the W, right, different value of W here, you can see the error also changes, right? And this looks like a big U shape. What you want to do is you want to find a point, find the W value that actually has the least amount of errors. that's basically a regression process. So coming back to that task, experience, and performance measure, that cost function is performance measurements. The task is to actually estimate these values correctly. Experience is basically you're trying different things, and you're actually plotting this error graph to actually make it better. Better meaning less error amount. Okay, so that is a linear regression. So the next is a binary classification. So what binary classification? The next one is basically the binary classification includes something called logistic regression, but I will tell you what it is in the later slides. So let's assume that, okay, let me explain what binary classification does. So the classification is basically is classifying whether this is true or false. Binary is basically whether it's 0 or 1. So you're telling, or you're actually classifying whether it is true or false in a very simple term. So basically, given the number of hours you study for your exam, right, you either pass the exam or fail the exam. Okay, so let's have very simple model like this here. So let's say we collect the data from the students. We ask them, hey, how much time have you studied for this exam? And for people who studied less than specific hour, failed. Students who actually studied more than specific hours actually succeeded and they passed. If we use the linear regression for this, it could look something like that. Okay, the line is actually drawn to its best. But then the problem here is that, so when we only have 6 data points like this, right, we have the linear regression, and because the fail and pass is 1 and 0, we draw a line from 0.5, because it's in between, and we hit here, and then we draw a line here. So basically, anyone studies less than this point will likely to fail. Anyone who studies more than this point will pass. But the problem is, if there's some student who likes to study a lot every day, so let's say he or she studies so many hours and he or she passed. Now what happens is that boundary, that we call it threshold, actually shifts to here because of this person. And what happens is that this person, even though he passed, the AI will say, hey, this guy is on the left side of this boundary, so he fails. And in that case, what happens is the AI is not performing well. It's actually failed to accurately estimate what that student would be like. So that's binary classification. So what people introduce, what researchers have introduced, is that, hey, we cannot use a linear regression when we are actually dealing with binary classification. So they introduced the concept of logistic regression, where the equation is like that, different from the ax plus b. It has some funky equation like that. What it does is that it draws the curvature like this between the 0 and 1. Okay, but as you actually change the weight or the other constant value, what happens is that the graph shifts left to right, and then the steepness of that slope will actually change. So if you actually took it a lot, it will look like a step in the near future. Okay. So if you actually apply that to here, what will happen is the line will look like that and then drop and like this. So it will the boundary will be kept constant. Okay. Again, we comes back to the performance measure. For the linear regression, we saw it's very clean and nice. But then logistic regression incorporates an exponential function, which is not a linear function. So the cost, if you actually draw the cost function, it looks very funky. So I'm not gonna go into much details, but there's a lot of algorithms to solve this as well. But the reason why I'm showing you this is depending on what you actually use for the so-called the algorithm, whether you're using the linear classification or logistic regression for the binary classification, the performance measurement has to be a little bit different. Okay. Any questions so far? Am I going too fast or is it okay? Okay, all right. Okay, so we're moving on. So the next one is about k-means clustering. So in the machine learning, we also have something called clustering mechanisms. Where, so for example here, let's say this is a two-dimensional coordinate system. Let's say here, this point right there, small one right there, is, let's say the x is about 0.8, y is about 0.5. So every dot here has its coordinate system. But let's say you want to represent this in a very simple way. Okay, maybe in a two-digit code, maybe look like this. Okay, so any dots belong in this area, we call it, hey, the dot belongs in an area called 0, 0. And for any dots actually belongs in this area, we call it, hey, the dot belongs to area 0, 1, and goes on and on. But do you see the problem here? Do you see any problem? Are you happy with this coordinate system that we actually made it very simple? So what happens to these people here? I mean, this looks like a one group, right? I mean, for me, it looks like a one group. But we actually divided them, right? We actually said, hey, even though you guys are together, you guys are with your friend, we're gonna just split you guys into half, right? And they are not going to be happy about that. So how can we actually make this, we call it the simplification, better, right? So one way we can try to do is, so you see that the location of the numbers has been changed, right? So we call it, hey, why don't we do this? We're still going to keep the 4 digits for the 00, 01, 10, and 11. We're going to keep those 4 digits still, but we're going to say, hey, if you belong around here, we're gonna call them a 01. If you belong around here, then we call it 00. And if you belong somewhere here, we're gonna call it 10. If you're around here, we call it 11. Still not very accurate, but better than before. So now you see the concept, like you see like how to actually group those data better. Okay. The term clustering is basically, it means grouping of the data, grouping of unstructured data like this. So here the K means how many groups do you need to represent the data you see here. So how many groups do you see? I see 5. Okay. So 1, 2, 3, 4, 5. So K, we set that to 5. So you see there's a 5 dots here. 1, 2, 3, 4, 5. These dots are just randomly spread it around. So we call it just, we rolled it randomly, right? And then what they need to do is they need to find the center point of each group to represent their group members. And the k-means is the algorithm to actually find them. So you can see that here at first, what they do is, we call it, it's the, how should we say? It's a war, it's a fight against different nodes. Basically, when you're fighting, when this dot is fighting against him, there's a battle line here. So we call that a battle line, and then we divide the areas into different sections. And then after doing that, what it does is that it actually, for this one, it tries to find where is the center of this battlefield, and we actually move it like that. So the dots actually move to different areas. And if you do this step by step, so I'll show you the example here. So you can see that these guys belong to the blue group, green group, purple, red, and black group. and you can see all these points here. These black dots, black lines are representing where this green dot or the other dots are going to move in the next step. So you can see these are not very happy, right? Because a lot of these groups are split into different groups. You can see progressively these groups move around. You can now see that the blue group is pretty settled down now. Now you can see that from here to there, the green group is also getting a little bit better. You can see that the green group is getting much better. Now the green group is okay. The purple and the black and red is not okay right now. But if you actually keep on doing this, you can see that step by step it gets better. I terminated the example here. I mean, if I do more, it gets better and better and better. But then now it actually delivers the concept of what this k-means actually do. So basically, what they do is they actually differentiate different group of data using something called k-means clustering. So for this k-means clustering, there's one big question that we need to actually answer. Does this algorithm always find the optimal clustering, optimal grouping between these groups? Not necessarily. Maybe if you can use your imagination, you can try to think of what would be the worst case scenario. It could look like something like this, right? So they could think, hey, this looks like a one group, but that actually small group looks like a two groups. You know, that could actually happen in the real life, and the solution to actually solve that problem is that we need to actually be careful about where these points actually start, and then we also need to run many k-means algorithm, meaning so when the algorithm starts, I told you that these dots are randomly spread out on the field, the battlefield, and then they need to actually find their groups progressively. But if you can also, okay, I thought about this idea. So maybe these are the captains, these are the soldiers. When they're spread out, the captain needs to find where their soldiers are. If the captain is thrown into some weird places, he's not gonna find their soldiers in a timely manner. So in that case, we need to actually run many different trials to actually find the optimum cases. Okay. Also, another difficult problem is, so if let's say you saw this data, right? This is a very simple one. So you can automatically figure out, hey, this looks like three groups, okay? But let's imagine you don't have this visualization, and what I give you is an x and y's, this bunch of coordinate numbers, right? In that case, it is very difficult to figure out how many clusters are there, right? Because I showed you this, you can say there's 3 groups, but if I didn't, then there will be some issues to actually figure out. So the difficult problem here is there is no easy way to find out what the right number of cluster is. So what you need to do is you need to actually run a lot of options. Like maybe you first try with number k equals 2, which means we are assuming there will be 2 groups, and let's see how accurate the system will be. Let's say this is the error is very high. As you increase the number of groups, you can see the error actually decreases, right? So you can see that, oh, okay, it seems like after the number of groups 6, the performance is about the same, so I can say, okay, the group, maybe I can just use k equals 6 as my optimum grouping number, okay? The k-means algorithms actually used very often used as a data analysis tool to figure out like how many groups of data, how many classes, how many categories does this data actually include. It could also be also used for the speech recognition. Like everyone here has different voice tones and different intonations and Amazon Echo is doing is actually they in their very early stage they actually recorded our voices, and they actually plotted the information to the vector, the 2D plot, and they use some kind of clustering method to figure out who you really are. And then also used for like color palettes, like in the graphical display devices, like they actually use this k-means clustering algorithms to figure out what is the color balance of this display and all that stuff. Okay. Next is the last algorithm. The SVM it's called support vector machine, but we have to actually tackle it from the linear classifier. So here in this case, you're classifying, so there is two groups here, the green members, the white members. So the linear classifier meaning that you need to draw a line, straight line, to actually differentiate these two groups. How would you do it? Likely you draw a line in between, right? Like that. But then there will be an infinite number of answers for that, right? You could draw it this way, you could draw it this way, and many, many more. But which one is actually the best? No one, you have to actually, I mean, everyone will have their own ideas, which one is actually the best, but then we have to, again, we have to teach the machine to figure out what is the best. So we need to be a little bit careful here. So in order to do this, people thought about, hey, let's use a support vector machine. I actually studied this when I was in university. I still don't like their naming sense for this one, but actually they call it support vector machine for some reason. I'll explain it later. But what they're trying to do here is the SVM tries to maximize the margin around the separating hyperplane. So it might sound a little bit difficult, but then what they mean is that this is a hyperplane. So that's the equation, that's the boundary. And what they're trying to do is they will have something called margin around the line, and they want to have that margin as big as possible. Okay. So a little bit more details. You can actually take a look at it later. So basically, what they're trying to solve is actually they want to find the best performing. They want to find the best performing program or the classification equation given the data set like this. Okay, so let's actually move on and try to explain it a little bit better here. So we draw, let's say there is a hyperplane, the mathematical equation boundary like that, right? We compute the margin. So basically, we call this data points, or we call it node, N-O-D-E, node. So for each node, we find, for the given hyperplane, we find the closest nodes, and we also draw a line like that. And we compute the distance. In case we have a line like this, we will have a narrower margin. Okay, so seeing that compared to this is much narrower. Okay, so here what we are trying to do is maximize the margin. Right, so this one is none. Okay, for this one, okay. So for this one, the margin will be much narrower, like this thin, about this thin. So this one could be also not the best one. So for the three options that we've seen, we can say, hey, this one is so far the best, right? So the margin is here. So why is it best? Because the margin, we also call it the safe zone between these two groups are pretty big enough, right? Meaning that I also always, whenever I teach these classification or deep learning, artificial intelligence, I always actually refer to the battle, the war games, and all that stuff. It's more easier to understand. If you imagine the red and blue is fighting each other, then they're, actually, they took a break on fighting. What you want is you want to have as largest safe zone as possible to actually avoid any future conflicts. So having that margin, having the safe zone, is the larger the better, basically. Okay. And speaking in more of a machine learning tongue, is better because it has more margin, meaning it is more robust to the errors. So let's say if the margin is very narrow, if let's say the data falls maybe somewhere here, right? Because the new data, maybe unseen data, is here. Because it's under here, we call it, hey, it could be the red ones. But let's say if we draw a line like this, very narrow margin, this one could be considered as, again, what, the blue one, right? As we see in logistic regression. So that has to be very carefully designed. So a little bit of math there. So how to compute that is there's a lot of equations on that as well. But simply saying it's basically you draw a perpendicular line to the nearest the data points, the nodes, and then you just compute the distance for that to get it done. We also have the concept of the sloped margin classification. So what are you going to do if you see data, something like that? This one is actually very close to the real life data set, right? You in real life you never see, you're unlikely to see something like this. It's too clean. Okay, so what happens if you see that? How are you going to draw a line around it? Okay, so that could be one idea. But then when this was introduced, the concept of having the curvature didn't exist, but then it was too complex. So what they did was they allowed the margin, allowed the errors, so that's why they call it soft margin. So the margin is there, the battlefield, the safe zone exists, but then they allowed, hey, okay, so there exist the outliers, so okay, we do accept that fact. So these errors were also considered into the performance measurements. So at the beginning, I told you that this SVM tries to maximize the size of the safe zone, but then whenever you see the errors like that, it actually deducts some points from the measurements the performance measurements that we had, and that is actually this technique, this support vector machine, was very, very famous until the deep learning. And then I used this in the first year of my PhD course, because I started my PhD in year 2011, and then in year 2012 the deep learning has advented, and then in year about 2013 it got really famous. So for that 2-year gap, I actually used this technique for my papers and all that. So it was very famous, and for most of cases, if you don't have a lot of data, if you don't have big data, this could work pretty well too. Okay, now we're finally diving into the artificial neural networks. So you might have wondered, okay, linear, logistic, k-means, SVM, why are we using this? The concept introduced in those four are all mixed in this area. So like all this, I told you about the battlefield concept of the k-means clustering, and that battlefield concept also applies to the support vector machine, where we try to actually divide different groups into between the safe zones. The linear regression, I talked about how to draw the line, right? The binary classification. Because the line doesn't really work, we have to actually make the curve, right? All that concept now actually mixes together with somewhat novel concept back then. So as the term neural network suggests, neural network is our brain network. Neuron, the artificial neural network, Tom says that the artificial, so it's a neural network, but it is artificial. So it's a made up artificial network, neural network. but then the component is a neuron inside. So this is a example of a neuron in our brain. So basically, any signals that is received by the dendrites travels to the axon, and then it fires to the other neuron at the axon terminal. But you might wonder, why the heck are we looking at the neurons when we're talking about computer science? But this is basically the concept. Okay. So any electrical signals that are received by the dendrites travels through the axon terminal and fires back to the other neuron, and so on and so on. And the group, the network of this neuron is called neural network. Okay. Before we move on to the network concept, so let's talk about the number of neurons actually. The human brains actually do have about 100 billion neurons in our brain. The fruit flies that we see has about 250k neurons. The roundworms that you see on the ground, or even smaller worms, actually have 302 neurons. Interestingly, the roundworms actually, performs better than any computer algorithms. Like in terms of survivability, like if you throw a roundworm onto the ground, it will do a very great job of surviving for a long time. But if you actually throw a robot equipped with some kind of AI into the muddy ground, it's not gonna survive. That's why like all this Mars, space travel, space actually exploration had a lot of. It costed a lot, but none of them actually have those intelligent functions that are actually able to survive in a harsh environment. But anyways, so the point here is that even the very small roundworms sometimes do perform better than the computers. And for the computers, the current capability could try maybe around 100k neurons right now. And however, again, the Moravec's paradox comes again. So there was a reason why I actually explained this, because things could be easy for the worms or humans, can be very difficult for AI to actually serve. So we call that general intelligence. So humans, fruit flies, roundworms have a general intelligence, like the experience that you acquired from something else could be transferred to another task. Let's say you are very expert in IKEA furniture builder, right? You went outside and you were trying to build a home. You never built a home, but you know how to use your drill, right? You know how to use your hammers and all that stuff. So that knowledge gets transferred, but then AI does not have that much. It's still an active research field. We call it a transfer learning, but this is another different topic. So if you're interested, I could discuss it with you later. So how does neuron work? So the image that I've shown you, the neuron here, right? The dendrites to the axon terminal. How does that actually work inside? It's like a dial with some kind of threshold and with a light bulb. Okay. So let's say you have in your home, you have some kind of dial, and you have to turn it some amount to make the light bulb light up. Let's imagine that. Okay. This red area is the threshold, right? So you have to turn the knob, turn the dial more than the threshold value to actually make the light bulb light up. And the light up thing, we call it as activation of the node. Okay. So let's imagine this is the neuron that we saw, and let's say the signal is coming in. The strength has to be strong enough so that the light bulb or the signal is transferred to the next neuron. Okay, did you get that concept? So incoming signal has to be more than a certain value to be actually transferred to the next node. Okay, so if you represent that in sigmoid function, it looks like that. So threshold is like that. So the input signal strength x increases. At a certain point, hey, the light bulb comes up, and then it actually lights up, right, and passes to the next step. But then problem with that is that in real life, not in the computer world, but then in the real world, the natural phenomenon does not have such thing. Everything has to be continuous, smooth. So we call that a discrete function, meaning it's not continuous, okay? And the real world functions like the sigmoid function. Okay? The stiffness of the sigmoid function, maybe it could vary, but then you can see the concept there. Okay? So let's put things together. So let's say let's say this is a neuron, let's say this is a dendrite. Okay, we have the dendrites like floating around, and we have the neuron here, the big body, and let's say we have the axon like that, and then let's say at the axon terminal, the signal goes out. Okay? So we receive inputs from another neurons, let's say input A, B, and C. We sum it all, we add them all up, and the added value x is transferred to the sigmoid function, and then the y gets output. Okay, this is the basic building block of the artificial neural network. So the neural networks conceptually looks like that. Okay, so a lot of different neurons combined. The signal, the yellow, the arrows are signals. So signal comes in, do some mathematics inside. The signals to the other nodes, signal to the other nodes, and it could have multiple layers and multiple nodes in the layers as well. So if we actually draw this in a mathematical way, we could actually make it like that. Okay, so the input, and all these circles are the neurons. We call it the node, right? And then the green arrows here are the connections. We call it a edge, or yeah, let's call it just edge, the connection for right now. So everything happens on each node. The summation and the sigmoid function, and the output goes up, goes out, goes out, and actually travels to the network. Okay. So I explained the neural network and artificial neural network, and now we have to ask a question. So what does this neural network learn? Okay, from the 4 algorithms that I seen you, right? The linear regression, logistic regression, k-means, support vector machine. It has its optimization method, right? The linear regression, we compute the distance, right? We try to minimize the error, right? K-means we actually move the captain, different areas to find their soldiers correctly. So what does this guy do? So here, the concept of learning here is figuring out the combination of weights. Okay, so this is very complex. So there's a lot of different weights combinations here, but if you actually conceptualize this in a very simple way, like linear regression, ax plus b, where x is also w, if you recall. We're trying to figure out what that w is. Okay, so that's what it's trying to do. We're trying to learn the weights, the combination of the weights, so that it actually performs really nicely on the given tasks. Having said that, I'm going to give you the example of how the inside of the artificial neural network actually works. I'm actually giving you these details so that when you actually want to implement something using artificial neural network, you actually need to understand what's actually going on. I mean, I can give you the code. If you ask me, I will give you the general framework. It's not difficult. I can give you, but you need to understand this to actually modify the code yourself when I'm not around and available to help, and to actually customize things as you wish. Okay. So let's assume very simple one: 2 layers. Okay, and then 2 nodes per layers. And let's assume that the input is 1 and 0.5. You might wonder, hey, what does that input represent? It could be something like, I've been working with Dr. Kim here, like if you have, let's say, soil property information, it could be, I don't know how you call it, but some property here is, let's say, given data x is 1, another property is 0.5, right? Given those properties, what we want to output is maybe some estimation for another property, okay? We have 2 lines here, but let's conceptually think of, okay, to understand what that input means, what that output means. And inside is basically, let's assume, it's a black box. It's not very observable, but then equations inside. Okay? So given those 2 inputs, let's say the initial stage, we have the combination of weights. These are basically preset. You didn't do anything. These are randomly selected weights. Okay, let's say you have these numbers. If you do the math, it's basically about middle school mathematics, maybe or around elementary, middle school math. Not difficult. So if you actually combine those, so in order to compute what is the input for this given node, right? So the input is coming from these 2 nodes, from this line and from this line, right? And the input for here was what? 0, right? And then the weight between these 2 nodes is 0.5, 0.9, so 0.9 right there. Okay? And then input from here for this one is 0.5. The weight between these 2 nodes is 0.3. So if you compute all that, you will get 1.05. I will give you the slide so you can now later take a look at it. So 1.05 right there, right? After summing up, the next step is the activation function, the sigmoid. So if you actually use this value here to here, this is a sigmoid equation, you will get 0.74808. So that is the input for this node. Like the one that has been made here, the input here is 0.78. It's even 0.7408. Okay? And the input for this node is also computed the same way. You can see all the numbers here. You can see that the output is, the input for this node is as follows. Okay? So now you can see, because this is the output layer, this is a final numbers that you will actually get. You're not applying any activation function here, unless you want to actually pass it down to the other nodes. Okay. So recapping again, learning here for the linear regression, the identifying the constant, the A or B, accurately is the learning for the machines, for the AI. So here the accurate, so what does the accurate mean? So accurate is the error. So we're saying, hey, the AI is very accurate if there is a very small amount of errors, right? And what does error means? Error is the difference between the predictions that the AI made and the actual answer, okay? Okay, if the answer is 2, but I predict 1, the error is what? 1, right? So that's computed. So here's the thing. So for the linear regression, very simple one. Let's say when we compute the error, right, and then the error amount is 1. That applying that error amount to modify the A and B is very simple. It's not that difficult. But how do we actually do this for the neural networks, right? Neural networks, we have this, right? Let's say for this output, let's say the actual answer was 1. The error is what, 0.2, around 6, something like that. How do we use that error, 0.26, and edit those weights? Could be a trouble. So we have something called backpropagation. So backpropagation here is basically you're propagating backwards. This concept here is forward propagation. We call it forward network, forward propagation. Now we're actually going back with the errors. So with the computed error, right? And let's say you would remember that for a given node, there are multiple nodes in the prior layer that affects the output of this node, right? How do we then propagate? How do we distribute the errors then, right? Do we use the ratio? Maybe a good idea to do that. So because the weight, right, affecting this node is 3, let's say this is 3, this is 1, summing them up is 4, right? There's total 4 influencing value for this, but then this line takes three of them, this line takes 1, so 1/4 and 3/4. So maybe that could be a good idea to adapt. So given error, which is the predictions, difference between the prediction and the answer, right? O1 is the output, the weight, and you can see all the notations there. And let's say the output, the error, is propagated to here, and then the error in the hidden layer is also propagated back to the prior layers, and so on and so on and so on. It actually flows back toward the input layer. Another mathematics. So what it does is that I showed you that we take the ratio, right, influencing factor ratio, and we propagate it back. You can see the equations there, but I think it's much easier to just take a look at the numbers. So I'm just gonna go through just one example. So let's say the error here for this node output is 0.8. Okay. So here E1 right there. I gave you the equations right there. E1 is right there, and by adding this here, weight 2.0, and this one right there is 3.0, right? So we add those two up, right? And then because we are computing this error, contributing value is 2, right? 3.3 plus 2, 5/2. Okay. And then also the error comes from the let me see here, error. Okay, so that let's only focus on this part. So 0.8 and compute that. If you actually go down to the actual mathematics, it actually computes 0.232, and that actually gets propagated back. You can see here that it gets propagated back, and it actually affects the weight here to update the value in the future steps. And that also travels back to the another layer once the computation is completed. At this point, you might wonder, okay, so these might take a lot of time because there's a lot of computation, there's a lot of steps and all that. So you might wonder, hey, is there any way we can actually, come up with the combination of a weight at once? Doesn't really happen for the neural networks. This equation is designed for figuring out neural network composed of 3 layers, where each layer includes 3 nodes. So total 9 nodes, and the equation looks like that. But in a practice, there will be tens of layers, thousands of nodes per layers. Imagine how the equation look like, when we have that much complexity of a network. So it doesn't really work. So you have to actually try it one by one. But that's how we thought of it later. But we improved that. The computer scientist community improved that approach a little bit. But then in the earlier stage, it was called brute force manner. So meaning that I'm gonna try all the combination until it actually works, right? It's basically, let's say you have a friend's smartphone and you want to hack into it, that you try all the combinations as possible until it locks up, right? But the problem with that is it's time consuming, right? Even iPhone has 6 digits, combination is a lot, right? So given, let's say, for example, let's say for a given network there is 18, about 80,000 combinations, right? And then let's say one combination takes 1 second to try, 5 hours, right? And the 18,000 combination is only when there's 3 layers, 3 nodes, per 3 nodes per layer. So even for a very simple one, it takes about 5 hours to break in. So doesn't really the brute force matter? I mean, okay, practically it works, but then the time is it takes too much time.
Excuse me.
Yes.
The weightage is now. Maybe you can go back to the first figure. Yes. So this weightage, you don't have to be that the total doesn't have to be 1, right?
Doesn't have to be.
Okay.
Doesn't always happen like that. Yeah.
So you can.
Yes. It actually, you don't control this weight.
Okay.
Actually, the only thing you can control is your data and answer. All these inside weights are automatically. So initially, it randomly selects the weight, and then as the deep learning learns, it actually changes its weights to an optimum.
Also, it's based on the error.
Based on the error,
back
yes.
propagate.
Yes.
Okay. Can you use both, the forward and back propagate until they learn?
Oh, it has to be used at the same time. So forward is basically, so given, let's say, an input for training, it goes forward. It actually produces the output, and the output is compared with the answer, and the error is computed, and then it back propagates. So the forward and back propagate happens at the same time.
Okay, for how long?
Depending on the system, depending on the complexity, a few million times.
A few million
Times, yeah. Even for my projects where we actually use images, 10 billion or a few billions. But then the computation is quite fast. But for image training, if the data set is very big, it takes about a day or 2. We are actually using very expensive servers, but they actually take some time.
But is there any work to optimize this?
Yes. Oh, wait, optimize the backpropagation?
Yes.
Yes. So basically, we try the brute force, but then doesn't really. I mean, it takes too much time, right? So what people propose is something called gradient descent. So we're not trying the combinations randomly, while we approach this more smartly. Yes, I will say. So let's assume that the x-axis here is a combination of weights within the network, right? So given combination, there is a certain amount of errors of the AI system, right? And let's say we actually know this landscape. What we want to do is we want to descend down to the value of performance errors, right? Optimally, what we want to have is maybe somewhere around here. So what we actually use is the fact that when you're at the bottom of the valley, the gradient, which is the angle, the steepness